this Illuminating Student Learning Pathways in an Online Fractions Game.
I might be short in this one. Let's see. Can everybody hear me? Okay, good. I'm short enough I don't need the weird choker mic. So, excellent. All right, well, I would say, starting out with this, that as Matthew started out saying, perhaps forgive me a bit on the learning side. I'm definitely coming from this more from the learning analytics side, and so perhaps forgive a little bit if the data mining part might be a bit naive. So just start with that. And we also are playing around a little bit with the idea of nanogenetic learning pathways, because I'm, by training, a cognitive psychologist. I was an elementary school teacher. I was very interested in these kinds of learning processes. A lot of the experimental work that I was doing was not getting me to the answers I wanted, and this is how I ended up in data mining and examining process learning. So, yeah, it takes a while. So this is one of the problems that I'm concerned with. We in the US anyway, certainly not in many of the countries you represent, but it's a problem for us, big. We have a problem. We are basically STEM illiterate. I'm on the plane often. People say, what do you do? I do math education. Oh, I hate math. I can't do math. Grown-ups who have the money for a plane ticket. If I said I do reading education, would they say, I can't read, I hate reading? No, it wouldn't happen, and everybody's okay with that. So this is a problem. We've been researching math ed and how we fix it for a bazillion years, and we still don't know the answer. So I think part of that is some of the limitations of our current methods, that a lot of our quantitative methods give us some great pre-post type results and a lot more complicated analyses than that, but are not getting us to the process as well. And a lot of our qualitative methods are really great about process, very hard to generalize from. So how do we fix this problem? Well, of course, you know what I'm going to tell you. We love big data, right? So you think about it, people have called it new microscope, but basically we've just got a lot more data because of the way we're doing things. I have no idea what just happened there. So there we go, I think. Yeah. And we're also hopefully, by using those big data, getting some better measures of learning and teaching. So a couple of places that I'm coming at this from. One is from a math ed, kind of what are the ways that we can teach fractions best perspective. And there's a lot of theories out there. People argue about them. I'm not going to go into it a lot, just saying two of the most common are a kind of part-whole theory like this, or a more operator theory, like 1/4 is, you know, the operator that you put on these 24 peanuts and you get, or M&Ms, and you get 6. So the other way that I come at it is from really a connected learning viewpoint. And, you know, how do we try to make better learning environments? Well, we want them to be production-oriented. We want them to be interest-driven and personalized. We want them to be social, whether that's face-to-face social or all of the many online social forms that we can. We want them to be open and shared, like Scratch. We want them to be not like this. We want them to connect across home and school. This cartoon is just a quick, it's not connecting. Beautiful snowflake comes into the classroom and, you know, turns into a boring drop of water like everything else. So we want to connect in and out of school, and we want to use the affordances of current technology the best we can, particularly those of us who are looking into the back-end log data from the environments that we use. That's one of my favorite affordances. And really trying to change this view of STEM from simply, okay, somehow we're going to mush science, math, and technology all together, and it's going to solve a problem, to a view that maybe is a little bit more like this in terms of things about diversity, community, bringing in folks from all over, really increasing opportunity in STEM. So working on that. Okay, so the example I'm going to use today is from a game called Refraction, which is based on one of the favorite ideas about how people learn fractions right now, which is splitting. And what is splitting? Well, basically, it's this. This is a level in Refraction. And, come on, there we go. Yay. Nope. There's the golden button. So, how do you play this game? What you got to do is power that 1/8 ship and the 1/12 ship using 1/2 and 1/3 splitters. Right? So you're splitting the laser in order to solve a fraction problem. And you can see this is me kind of playing around. Some of the challenges are mathematical, some are spatial. I'm going to run into that rock. But I have to figure out that 1/8 is a half of a half of a half. That's really the core of splitting. Repeated halving, repeated thirding, repeated pieces. And again, back to the spatial challenge. Right now I've hit it with too much, so it's kind of jumping up and down like, ah! If you hit it with too little, it kind of looks sad. And another spatial challenge. Nope, can't use that one. Got to have something to rotate it. So kids really stick with this game for the spatial challenge. It's fun. They're having a great time. But they also, luckily, learn fractions. And yay, we did it. So this is the level that I'm going to tell you a lot about. It is a level where students are solving, they have to make a 1/6 and a 1/9. And we give it after they've done some basic game mechanic levels as like a pre-level, and then we give it at the end of the game when they have done about 30 different levels. This is a pretty hard level for two reasons. One, kids are really prone to go to 1/2, and they, it's just a fraction that actually makes sense to them, so they really want to use the 1/2 splitter first. If you use the 1/2 splitter first, you can't make 1/9 out of 1/2. The other reason that it really has a draw to 1/2 is there's two ships. So they think, if they're thinking part whole, they think, oh, got to split it in half. So when we got into our analytics on this, the overall goal was to start thinking about how do we define what do kids know in this game, what is mathematical knowledge here, and how do I know if it's changing? So first thing we did really was to have to say, okay, what's a mathematical state in this game? You saw those benders and rocks you can run into, and we said, you know what, we don't want to focus on, and some of our folks in Washington, the University of Washington, our partners, are working on the more, the whole game analysis using learning analytics, looking at the spatial challenges and the mathematical. We really, since obviously I'm a math ed researcher, wanted to look at just the math and just the learning. So we said, okay, well, here's a mathematical state. That's a laser just going off into space. That's where they start. That's a 1/3 splitter on a laser with the three pieces either, we don't care, we're not paying attention. They could be hitting a rock, they could be going into space, they could be doing anything on Earth besides hitting one of the mathematical targets. And that's the same for 1/2. Here, when we get into the mathematical targets, so what this means is, the little red box, is that the student is hitting the 1/6 ship, or the 1/9 ship, but with the incorrect amount. That's why it's red. So then here is the final state of the game when you've actually solved it correctly and you're doing 1/6 and 1/2. And 1/9. So I'm going to go through. We started with some ways of visualizing these levels. I'm going to go through this a little bit quickly. And this was sort of a second iteration. It doesn't give us everything we want because it doesn't show the process as well and as many times as people repeat. But what we wanted to be able to see was this 1/2 space and the 1/3 space in a kind of abstract way, and then be able to look and see where a kid was spending their time in the 1/2 space or the 1/3 space. And that's what this shows. That's obviously a much simpler situation there. So then using those mathematical states, we just started doing some, after visualization, some association rule learning. And this is basically, I think of it as like the supermarket example. If you buy onions and potato chips, what else do you buy? You buy burgers. So we kind of took burgers as our success state and used that to see what was associated with it. So what is really cool here is that we found that on the pre-level, when kids don't know a whole lot about this and they're just messing in the space, that the most highly associated states with the highest confidence were things that just use thirds at all. Not necessarily in a looking like a productive way, but just use thirds. And the only thing associated with success on 1/2 was very correctly using it to solve the problem. In other words, working in that 1/2 space was not the conceptual part that kids needed to do. What they needed to do was be working in the 1/3 space. Oops. And then on the post level, kind of a similar thing. What we found was that here, there's like 1,000 rules that are associated with a successful one. Most people succeed on the post level, and they don't on the pre. So there's like 1,000 rules related to this, but it's making 1/9 at all anywhere in there that was really important for the post. So essentially, what are our conclusions here? That messing around with 1/3, which is the central conceptual hurdle here, is really productive, even if you're not doing it to actually achieve an obvious goal right now. So looking into that process deeply, what do they need to do in their process to be moving in a good direction? And messing with 1/2 was pretty unproductive unless you used it just to get to, you have to use it to solve the problem. But playing in the 1/2 space was not productive. So we said, okay, we want to know more about this fussing. So we pulled out some variables on these board states, which are those mathematical states I defined before. Just straightforward things, for a level, the number of unique board states, total number of board states, average time on a board state. So these are all variables related to how much fussing with these board states they do. And we found 4 basic patterns, typical hierarchical cluster analysis, yada, yada, yada. You can get more details, come ask me later. And we found these 4 basic patterns. The first one is a haphazard pattern, where they're just like doing all kinds of stuff, but they're not really succeeding. The second one was still a fairly active pattern, but they are succeeding more often, and they more quickly get to the 1/3 space that I talked about earlier. Careful group really kind of is just going to the solution. Boom, boom, boom. And then we have this minimal group who kind of looks like the careful group, but they're not really succeeding. So we're not really sure what that is quite yet, and we're playing around with it. But what we did then was relate the cluster analysis results to our pre- and post-test external transfer tests. These are typical fraction tests, the kind of stuff we want kids to know about fractions, that kind of like, well, they're a little bit more exciting, they're interactive, so they're a little bit better than just a standard in-class fraction test, but they mine the same data. And what we found is that there were 2 states that were kind of unproductive. They did not predict good transfer scores. And those were the haphazard state, so lots and lots of fussing, and the very, very minimal state, so little exploration. And the 2 states that did really predict great transfer, good learning over the course of it, were the exploration states and the careful states. So, where are we going? So it was kind of cool to find out that fussing with the core concepts was really productive around that 1/3 space. And fussing at kind of this medium level was productive, but it's not a question. People are often asking me, well, what, do you want kids to just do stuff all the time? It's like, well, no. There's also a careful strategy that's productive. But there are fussing and really careful strategies that aren't very productive. So, our next step, of course, is to take this towards and making this environment adaptive and being able to say, what degree of fussing, for whom, and at what time, and then take it into, and our next steps, this was a great pairing because our next steps are straight into the sequence analysis of those board states the same way that Matthew was talking about they've been doing with the courses and the order of courses. So there's a bunch more kind of next steps that I could talk about in terms of we're looking at this with engagement, some Ryan Baker's work. We're actually looking at it with neuroscience as well, so we're going to be able to map these patterns to the brain activity patterns of students. This was one of my students who volunteered to put on the silly hat. And this is a NIRS machine, so it's a lot more tolerant of movement, so we can do that a lot better. So, and then, of course, there's developing teacher tools. It's one of the biggest issues we have about a lot of these games is that teachers say, well, my kids are just playing a game. What did they learn? So we're mapping these onto the Common Core, and teachers will be able to look at that and see what their students have learned from playing the game based on that back-end game analytics. So I'll end there, and if you have any questions. Hi, Ryan.
Hi. So I can just yell. Great work, Taylor. I had a quick question, which is going back to the haphazard and minimal and the fuss. That slide. Go back forward.
Going haphazard?
Yeah, the correlations to the pre-post. So how strong were they, and is there a sense where haphazard was worse than minimal or vice versa?
Actually, minimal's worse than haphazard. That interaction doesn't reach significance. The effect sizes are really nice on it. I don't remember the exact numbers right now, but the effect sizes are really nice. And the interesting part too, though, is that we did the same clustering using the data, and everybody has a cluster score for their pre-level and their post-level. So one of the most exciting things to me is that their pre-level does predict their pre-test score directly, but it doesn't predict their post-test score. So whatever you're doing here, whatever strategies you're using, and it's also interesting because that's also true on the post level. Now, I think that what's going on with the post level is that actually most people are using pretty productive strategies. They've changed to do more productive strategies, so that's why there's no association. But it's really nice that even if you come in doing nothing useful here in the beginning, playing this game for a while and getting used to it and learning it is going to change, is not going to mean you know, it is going to help you learn from on standard fraction tasks. Big room, a lot of running.
Yes. There was one here, closer. Yes.
Hi. I like this too, but I have a question. Games are strategic. People choose their moves for particular reasons. What do you imagine are the reasons that the students are following these patterns?
Yeah, it's a great question. We are actually developing what I call cross-method validation. I'm sure a lot of you are doing this, and I'm sure other people are calling it other things. I would love to get together with a group of people talking about it, because one of the things with data mining that I've dealt with often with a lot of my friends from computer science is, oh, well, you got the pattern, so it must be real. And I'm like, really? So actually what we're doing this week is we've turned these into, actually, Ryan, we're using a very similar protocol to our engagement protocol. We've turned these patterns into observables in the classroom. And so I have a team out who are looking at kids playing refraction and saying, do we see any of these patterns? And then we also have an ethnographer doing field notes of the classroom so that we can kind of validate if, you know, we do see these, if these really look like something real in the classroom or if it's just an artifact of our data mining. And we have done this already in a couple rounds on smaller data sets. And we've refined a lot of our patterns. For instance, a haphazard pattern that popped up earlier, we thought it was all haphazard. We didn't realize that there was a difference between haphazard and exploration until our ethnographers went out and looked at kids playing the game and said, you know what, there is a group of kids who really, they don't know what they're doing. They're just like, blah, blah, blah. But there's another group of kids who's saying, hey, I want to see if I can make a 132nd. And they're using every splitter they have, but they're trying to do something. They're experimenting with the space of the game. And so we could tweak the difference we found in the two was that the group who really was haphazard had a lot of repeat moves. And the group who was exploring in a more purposeful way, but still all over the place, didn't. They have very, very few repeat moves. So we could quickly tweak our algorithms to pull those two groups apart based on what we learned from taking this and going back to reality and saying, where's that mapping? So we are trying to develop that method, and really anybody who wants to talk about it, I'd love to.
Yeah, hi, I'm Bjorn from Brandeis University. I was wondering if you had some comments on like just the training factor of having played around with the game and just become better at doing the problems because you're now good at the game itself, but not specifically having learned the knowledge that you're trying to.
I think we have a lot more of that to unpack. We're working quite hard on, and this is something I'm collaborating with a bunch of folks on trying to think hard about, game analytics. I mean, how do I take what a kid is doing in a game and say if it's knowledge or it's just behavior patterns or whatever. So we're working hard on that end of it, but that's also why we keep that pre-post there, right? These kids are learning fractions from this game. They're not doing anything else around fractions at the time they're playing this game. They're, you know, at least on a pre-post level, they're learning it. Now, finding a control group, that's a different story. We played around with some games as control groups, and as an experimental psychologist, I'm not satisfied with any of that. I'm not satisfied that I can say, well, but maybe this game's just more fun, so they're learning more. Or maybe, you know, so finding the right control group here for a test of that learning gain compared to another group. I mean, I could do the standard, just compare them to kids doing nothing, but that doesn't really feel very satisfying either. So, thanks.
And one question I would have is, can you use the learning analytics to improve the design of the game? And so there's a reason why I ask it, because I was very puzzled, and I still am, why you include the spatial difficulties if what you're going for is helping kids to learn fractions, because it seems to make it more complicated, right? And I'm not sure that it contributes to the learning goal.
Early on, we worked very carefully with the development team to reduce, because the first thing we noticed in our first, what I would say, cross-method validation study was the kids were not struggling with the math at all. They were struggling with the spatial part. And we first identified that from the math background, kind of the analytics work we did. And so we've tweaked that so that the spatial, because the spatial is what's fun. I mean, it's not, I might find the fractions really, really fun, and kids like making their ship go boo, but the spatial challenge is a really fun part of it, and keeping them engaged is really important. Now, one of the studies we're about to start with Ryan, actually, in terms of the engagement part and looking at that, is being able to see if, map the learning and what's going on in the activity to the engagement data from the back-end data and be able to tell, well, are these spatial challenges really engaging, or maybe these rocks are just annoying people? So we'll be able to start looking into that more deeply and feed that back to our game designers as we're working on. At this point, we're really not redesigning refraction that much. We're working on designing new games and moving it into the teacher portal, but it informs all of those levels.
Hi.
One hand way in the back that keeps going up.
Yep. So hi, Taylor. David Schaefer from the University of Wisconsin.
Hi, David.
I like my colleagues here, like the work that you're doing. My question is, the different categories that you have, so haphazard and minimal and so forth, in order to run the regression equations, how are you characterizing those? Are those hand-coded? Is there what determines whether a student's pattern falls into one of those categories or another?
It's the variables. It's a standard hierarchical cluster analysis with those variables in it. And we can pick a lot of different variables. We played around with different variables, including and excluding, and so far this cluster solution, it's a nice happy cluster. It's Ward's clustering, but it's a nice happy solution for everything significantly different from everything else, and yada yada yada, and all the Duncans come out looking nice, and we can see big differences there, and it seems to capture something. But that's the basic method.
And would this generalize to a non-closed form domain? Meaning, if you didn't have a set of discrete states, would you expect you'd get a similar?
If I didn't have what? Sorry?
If you had a non-closed form domain. So in this case, those trees they completely map the space, right? If you had a domain where there were where the states weren't, where every state wasn't as easily determined, would you be able to use a similar?
I think you definitely, I'm doing similar work in a lot more open-ended environments like programming in Scratch. It's more difficult, but you have to, and the key is just what's your grain size. So the grain size we're going for right now is level. The grain size I want to start going for the sequence pattern mining is mathematical state and sequence of mathematical states. But for Scratch right now, we're looking at just, basically starting with a whole project and creating variables that are at the level of the whole project. But you just have to decide what level your variables are at. Are they going to be at the whole project? Or are they going to be at, so another of my environments is called iPro. It's a virtual robotics programming environment on the iPhone, and it's a touch programming environment, much simpler programming language than Scratch. And so for that, we can really clearly define program states in terms of similar to these mathematical states every time the program's changed. So then we're going to have variables at the level of program state, and actually we have a paper coming out in JLS really soon on that. So we're scaling it up to different levels, but you just have to define that, right?
Hey Taylor, Alyssa Wise, Simon Fraser University.
Hi Alyssa, where are you? There you are.
I'm the voice from above.
Yes, I know. I was like, wow, the room is talking to me, and it sounds like Alyssa.
So, as everyone said, very, very interesting work. One thing I saw in here that I thought was particularly interesting and perhaps a bit novel is this notion of situationally dependent productivity of patterns. Or that's a long term for the fact that what you were saying is that if I'm someone who's...
I like it, though. Can I use it?
Send it to you later. This idea of I can be an explorer, and if I'm exploring in the 1/3 space, it's really productive. But if I'm an explorer and I get stuck in the 1/2 space, it's actually not doing much for me. And I was interested if you've thought about or gone down the path of sort of detecting, I'm an explorer, but I'm stuck in the wrong path, and ways to provide feedback because I'm doing the right sort of thing, but because of the context, it's not actually doing what we'd hope it do.
That's definitely one of the first steps we want to take towards, and this also goes back to informing the design of the environment, because the next step for these games is for them to be adaptive. And so that would be one of the first things I will pull out of this, is saying, okay, if we identify, hey, somebody's acting like an explorer, but they're in the wrong space, and it's going to be a different space for each problem based on whatever the conceptual challenge is, and they're in the space that they shouldn't be in, and they're wasting time in, how do we kick them over into, a more productive space? And so another thing we're doing kind of in the classroom right now is investigating what kinds of feedback help make those changes happen. So, we kind of know what it looks like when kids are doing, particularly this level, which we all know backwards and forwards, when kids are doing this level and what kind of space they're exploring. And so we're just trying out hints, honestly, right now to say, hey, what if you tried that 1/3 splitter over there and where you put it? That's a simplistic example, but, kind of develop that in a naturalistic way because it's a game. You don't want to come in and be like, that's wrong. No, don't do it that way, right? You're wrong. You want to keep the game fun. And part of it is we actually, Zoran Popovich is my colleague who we developed this game together, and they did some experiments early on with, you saw the coin on one of those levels, you can get that extra coin. And what they found was that kids were spending way too much time on the coin, and that was keeping them in some negative spaces. But what that suggests to me is, hey, what if we put the coin in a place that might be likely to help them, to direct them towards the exploring in the right space? Because they definitely want that coin really bad. So if we made it about the 1/3 space instead of the 1/2 space, maybe that could make a difference. So trying to come up with ways to make games adaptive that are not just like kind of heavy-handed coming in and saying, go do this. So, and yeah, you should write that down, that term. I'll put it in my next paper. Thanks, everybody. Hey, Zach, we have met before.
Yeah, at the Learning Analytics workshop.
So now we're having a lunch break. We have to direct you to the lunch restaurant, actually just around the corner.
I've been seeing everybody's names everywhere, and I was like, have I met Zach? My name sounds like I know you're,
Yeah, we met a while ago.
Yeah.
And then we bumped into each other with me and Emily.